All right, welcome to lesson 24, and now we're talking about the limit of a function. And this is kind of your first introduction to calculus. So limits and calculus are synonymous with each other. What's your goal today? First of all, I want you to be able to use your own words to explain what a limit is. And then some of the skills we talk about today, I want you to be able to evaluate the expressions. You need to explain what a limit is, and then I want you to be able to evaluate some simple expressions. All right. So, what is a limit? Limit is an investigation of what happens to the value of a function, so we're looking at the y value, as x approaches a value of particular interest. So we want to know what's happening to this function when x is getting closer to 3 or 7. So that's all we're really doing. It's just a simple investigation. What's our notation? The notation is going to look like this. So LIM, and then underneath it, our x value approaching a of the function f of x. So we'll start with the easy part. This is the function under investigation. And this is the x value of interest. And then the LIM just indicates that we are dealing with a limit. All right. And if you were to speak out loud, if you want to ask me a question, the oral reading of this is the limit as x approaches a for the function f of x. And that's how you'd read that out loud. Okay? So there are a couple of properties to remember here when you're dealing with limits. So we have the sum difference of limits. So let's say I'm asking you to investigate the limit as x approaches a for two functions, f of x and then plus or minus g of x. Doesn't matter whether it's adding or subtracting. So I want you to analyze this big ugly function that's being added or subtracted. You can actually break this apart, and you can analyze each function separately. So you could say, okay, what's happening with function f of x? And then I'm going to add that result to what's happening to the function g of x. So you don't have to analyze it as one massive blob. You can break it down into its two components and look at it that way. Multiplying by a constant. So if you're analyzing the limit of a function and it's being multiplied by some number out front, you can get rid of the number and just allows you to have a scaled back version. You're not dealing with such big numbers. Oops. I should maybe move the constant. So the answer is going to be the constant multiplied by whatever the limit is, or whatever the answer is. So you just find the limit, and then you multiply it by that constant afterwards. Product. Product works very, very similar to your sum and difference. So let's say I am giving you a factored form of f of x, g of x. So it's broken into two functions. And I want you to evaluate it. And rather than expanding it or whatever operations, you can simply break it apart again. And you can find the limit as x approaches a for f of x. Find that result. And then simply multiply it by the result as you analyze the limit for g of x. So you can chunk it apart. It just makes it a little bit easier to work with. And similarly, the quotient rule really goes along with the product rule. So if I'm asking you to evaluate the limit as x approaches a of a rational expression, you can simply say, all right, I'm just going to analyze the limit of x approaching a for f of x, and then divided by the limit of x approaching a for g of x. And that's assuming, again, you can't have a denominator of 0, so g of x not equal to 0. Your power of limits. So if we have the limit, we're analyzing limit as x approaches a for a function that is to an exponent, so f of x to the exponent n, we can write that. I'm going to shrink that down, make it fit here. We can just simply go ahead and evaluate the function inside. So the limit as x approaches a of f of x, find that result, and then apply the exponent. Again, just allows you to deal with a scaled down version of the value. Okay. What happens if we want to find the limit as x approaches a for the nth root of f of x? So what you can do, instead of working your way through dealing with a square root, you can simply take the result of the limit as x approaches a for f of x, because we're interested in the function f of x itself, and just take the square root of your result. And finally, the constant rule. If you're trying to find the limit as x approaches a for some constant c, the answer is just going to be the constant. So if the function is y equals 5, what's happening when x becomes 1? What happens when x becomes 2? It doesn't matter. It's always going to be 5. So when you take the limit of a constant, it's just the value of the constant. So those are just some rules and tools to use as we start evaluating functions. And today we're looking at more of the simple ones to deal with. All right, continuous function. A continuous function. A function is said to be continuous if. So if we're talking about a polynomial, p of x, we say that it's continuous if the limit as x approaches any point on this function, f of x, is simply equal to substituting the a value in. So what that's basically saying is that we have no problems. Okay, so no, we'll call it issues at this point. Not dividing by 0, not taking the square root of a negative, and so on and so forth. Any rational function, so we're talking about a rational function now, so one divided by another, so exactly what you're doing last in the advanced functions. Any rational function in that form, where p and q are polynomials, it's said to be continuous at every value of a such that q of a is not equal to 0. So what does that simply mean? It means that if you're analyzing a rational function that looks like this, it's rational if there's no problems. So I can just simply substitute the a value in and into both the p and q function. And again, q of a cannot equal 0. So if you get a value, if you plug in a value into a function, and I'll explain that in the examples here, it's continuous if there's no problems. So again, no issues. All right, and we're going to do some examples here. So essentially, a continuous function can be defined as a function that when you graph it, you can trace without lifting your pencil off the page. If you have to lift your pencil off the page, it is not a continuous function. So I got a couple of examples, and we'll get through a few of them before I run out of time here. So the limit of x squared plus 4x minus 3. We want to look at it as x approaches negative 2. So the first thing I ask myself, is there a denominator? The answer is no, so that's a good thing because odds of a problem occurring are pretty slim now. So what am I doing? I am plugging in my negative 2 value into this equation. And because I can calculate it, it spits out a number. I get negative 7. Then the limit of x approaching negative 2 exists. So that means that at negative 2, this function has a y value, and it's negative 7. For the second one, very similar. I don't have a denominator, so I'm not too worried. So I'm going to go ahead and do my substitution. So negative 1 plus 2, negative 1 plus 5 squared. So I end up with negative 1 plus 2. So that's a 1. Negative 1 plus 5 is 4. Square it, runs through the calculator, I get 16. So that means if I was to graph this function, which would be a cubic, at negative 1, the value of the function is 16. So it does exist. So all we're doing is we're just basically looking at what's happening at a particular value. Started off with easy ones, and you're asking yourself, well, this is just substituting in. Yeah, exactly. For this one, and you don't want to copy this down immediately, hold on for a second. I'll tell you when you can start copying. So now let's do the substitution. 4 minus 2 squared over 2 minus 2. 2 minus 2 in the denominator creates a problem. We cannot divide by 0. So here's where limits start playing a role. Okay? Cannot do it this way. So what we need to do is we need to go back to our tool bag and use some of the skills that we've got before. How can we kind of work our way through this or avoid that problem in the denominator, 2 minus x? Well, we can, one of our tools that we have available to us is factor and simplify. So for the majority of homework today, this is your go-to. So if we have a problem, which we do, we have to factor. Denominator's factored, can't do anything with it. The numerator, though, is a difference of squares. 2 minus x, 2 plus x. 2 minus x will simplify. So now I'm evaluating the limit as x approaches 2 for 2 plus x. I ask myself, do I have an issue? No, I can actually go ahead and calculate that, and we get a value of 4. Okay. Now, before when you're graphing it, it would have been an asymptote at x equals 2, and there still is an asymptote at x equals 2, but what we're looking at with the limit, it appears that this particular function would be approaching a value of 4. And we're going to talk about that a little bit later on. Okay, so it's not, we're not eliminating an asymptote if that's what you're concerned with. We're simply evaluating what the function looks like it's approaching as we approach it from 2. Okay. The third one, or sorry, number 4, when we look at it, do we have a problem? So before I do substitution, I start looking at my denominators, and I'm like, yeah, there's a problem here. I can't put 2 in. So that means I can go to my factor and simplify. So the limit as x approaches 2, and yes, the notation has to occur. You cannot, and this is what the notation has to look like. The top will factor to x minus 2 and x plus 3. And x minus 2. And when you do the simplification, the limit as x approaches 2 for x plus 3, do I have a problem? Absolutely not. Plugging it in, I get a 5. Now, let me go back for a sec, because I said something that was misleading, I realized. You're saying to yourself there should be an asymptote there, and that's an incorrect statement. I'm hoping there's a couple people that said, no, that's not true. Because if this occurs, okay, if you factor and a term falls out, like these two, what is really there? Okay, it's not an asymptote, it's actually a hole. Okay, so put that down here. When terms cancel, you have a hole. So what does that mean? It tells you the location of the hole. So the hole, and this is beyond what, I'm not too worried about this today, the hole is at, in this particular question, 2 and 4. So there would be a hole at 2 and 4. Here, there would be a hole at 2 and 5. All right, so it's telling you the location of the hole. So it appears that if you were traveling along the graph, when you get to x equals 2, so when I get to x equals 2, I would expect my y value is going to be a 5. And that's what limits do. It's analyzing, predicting what will the y value be when you get there. All right, we already know it's a hole there, but we have an anticipated value, and I'll talk about how we can determine or what role this is going to play in a couple of seconds. So I'm going to do the next finish a couple of examples up in the next video.